Take a look at how much of a mineral we can dissolve into an aqueous solution, namely one that is dominated by H2O. So let's say we have some mineral and it's sitting here in a container of water. Well, we'll take the example of fluorite, CaF2, so that's a Ca for calcium, and we can look up in a table that its equilibrium constant, or rather the solubility product, Ksp, is equal to 3.9 times 10 to the minus 11. And in another video, we talk about what KSP means and how it's derived. So for the case of dissolving a mineral in an aqueous solution, we can use this KSP to determine how much that mineral will dissolve into the water and how much would be left behind. So let's start with the KSP itself. So we have the value, but what does it mean? Well, it represents the concentration of calcium 2 plus ion, that's a plus, in an aqueous solution, multiplied by the concentration of fluorine minus, also in an aqueous solution, AQ there, and that will be squared. The reason it's squared is because when we write the equilibrium CaF2 solid dissolving into an aqueous solution, we get calcium 2 plus, and then in aqueous solution plus 2 atoms of fluorine, and then also in an aqueous solution. So since we have a 2 here as a coefficient, we're getting 2 atoms of fluorine that are dissolving out when we dissolve fluorite into water. That means that that coefficient now becomes an exponent in the solubility product or any other kind of equilibrium constant. So the solubility product is this. We're going to assume that the system is ideal. So these were in theory, they are activities. We'll let the activity be equal to the concentration. And then this whole thing is equal to this value up here, 3.9 times 10 to the minus 11. Well, let's do this. Let's let the concentration of calcium in aqueous solution be equal to X, and let X be in, let's say, moles per liter. So we'll just have M for molarity. So if calcium, the concentration of calcium is X, then looking at this equation here, whatever the concentration of calcium is, we would have 2 times the number of fluorine atoms. And so that means that the concentration of fluorine atoms in the aqueous solution would be 2 times X. For every 1 mole of fluorite, we get 1 mole of calcium ions and 2 moles of fluorine ions. So if we let this be X, then this is 2X, and then the amount of fluorite involved is also simply equal to X, or 1X. Let's erase the chalkboard and take a look at the calculation then. So the KSP is equal to the concentration of calcium. We'll skip the superscripts and subscripts. So this is all in aqueous solution. The fluorine is 1 minus the calcium is 2 plus. So we just have this calcium times fluorine squared, but then we're going to let this be equal to X. The concentration of fluorine is 2X. So this is going to be equal to X times the quantity 2X squared, and that whole quantity is equal to 4x cubed. So we can now write 4x cubed is equal to the numeric value of the KSP, which is again 3.9 times 10 to the minus 11. If we take this, we could solve for x. We can divide by 4, and we can undo the cubed by taking the cubed root, which is the same as raising it to the 1/3 power. And that whole thing would be equal to 2.1 times 10 to the minus 4. So remember, this is our x. So x is equal to this. And we said x is also the concentration of calcium ion in the aqueous solution. So what is the concentration of calcium ion in the aqueous solution? It is 2.1 times 10 to the minus 4 molar, or 2.1 times 10 to the minus 4 moles per liter, the definition of molar. Let's say we wanted to know how much fluorite is dissolved. And we wanted to know in terms of the mass. Well, remember, X is the number of moles involved, and so whatever the number of moles for moles of calcium we have the same number of moles of fluorite. So for fluorite, the amount that we would dissolve would be 2.1 times 10 to the minus 4. That's in moles of fluorite per liter. We would want to know the number of grams, and that would require canceling moles. So we need to know the number of grams of calcium fluorite per mole. And that just means we have to insert the molecular weight. The molecular weight for fluorite is 78.1 grams per mole. So we multiply this out by 78, divide by 1, which is trivial, and we end up with 1.6 times 10 to the minus 2 grams of calcium fluorite per liter of solution. This is a really important number to us. So, because it really tells us whether or not this number applies at all. So long as we put into our container of water more than 1.6 times 10 to the minus 2, or let's just write it out as a decimal, 0.016 grams. So long as we have more than 0.016 grams of fluorite that are put into the solution, then not all of it will dissolve. We'll have a little bit of calcium fluorite that's left over that's undissolved, and then we'll have this concentration of calcium ion in solution. And you could find out the concentration of fluorine using that same number. Remember, the concentration of fluorine is equal to 2 times X. So if the calcium concentration is 2.1 times 10 to the 4, then the fluorine concentration would be 4.2 times 10 to the minus 4 molar. So we know the concentrations of these, but we only know the concentration of fluorine and calcium because not all of the fluoride has been dissolved in the water. We have to have some left over. If, let's say, we put in less than 0.016 grams of fluorite into 1 liter of water, if we have 1 liter of water, but we put in 0.0, let's say 0.02 grams of fluorite, all of that material will dissolve. There will be no calcium fluorite left here. It'll all go into solution, and then the concentrations of fluorine and calcium would all be less than what we've calculated here and here. So a very important limiting factor in using these KSP values is that when we're calculating the amount of a material that's dissolved, if we have less than that amount, then the concentrations we've calculated are simply maximum values that will not be achieved unless we add more stuff until the system is so-called saturated. So we'll just finish up this video with this last concept. The system is saturated when not all of the calcium fluoride is dissolved. So we have some left over in solution that allows this KSP value to work. So the KSP values, these solubility products, and equilibrium constants in general only work when we have all of the phases present. Then we can use these values to do these kinds of calculations.